while in a descending orbit. That is just the way the images get acquired. That's the way the satellite works. Now, so there is not, in that sense, it's not designed to have a benefit. That's how it is. However, one benefit that you have is that you can see the same scene from two different angles, which can be quite beneficial. If you combine ascending and descending, you also get a higher temporal resolution, right? Because one time you see it ascending and then you see it descending, so you increase your temporal resolution if you manage to process them together, as in the other question. Considering the layover effect, can we use optical imagery to compensate for the missing data? Well, I mean, can we? One could probably develop a kind of method, but I don't see any use in that. Okay. Like, what would be the data that you get, and if you combine two sensors that actually see and image very different things and very different targets? You have to be, very careful in thinking what you actually trying to want to achieve, right? So I don't really see any useful application for that. Is it possible that we can use the concept of unmixing problem in SAR image? I have to say I don't really sure what's the unmixing problem, so, or the concept of unmixing problem. So again, maybe if you can specify that more clearly. What pre-processing step must be performed for further performing the coherency matrix? And how can I geocode image for visualizing the scene properly? Now, the coherency matrix, we will come to that at the very end of the lecture. Okay, it's a very advanced topic, so we maybe can talk about that then. But geocoding is an interesting point, because I'm not really mentioned that yet, and I found out I did not have any. It's not part. I didn't mention that. Although that is an interesting point, and it's not as easy in that sense. We come today. Actually, today we will come to how we can geocode very, very precisely, right? But I never really talk about the process in itself. So first of all, when we talk about geocoding, that we have to with satellite data. Okay, we typically we need to know the orbit very well. We process that in a geocentric coordinate system, follow the orbit data. We know the time of our acquisition. From that time, we can then, with the orbit data, we can pinpoint the precise position of the satellite at a given time. We know the direction the satellite is looking at. So in that sense, the positioning that is then the positioning in the azimuth direction, that is mostly dependent on the quality of your orbit data and the quality of your timing data that you have. Now in range, it's a bit different. What we have in range is
recording in progress.
Yeah, no, I cannot get rid of that boxes. Okay, so all right, let me come here. So what we have in range in this direction, our position is actually ambiguous. Okay, that's the problem of the layover. So you know the time information, okay? So you know, let's say at point A, you know the distance between the sensor and point A, okay? But actually that point could be anywhere on that circle, okay? All right, it could be anywhere here. So what you need to do then to precisely geocode is that you, if you have a good DEM, okay, if you have a DEM, for example, for point B, then you can pinpoint and you can say, well, wherever that circle that we have is then intersecting with the DEM, that's where my point is, okay? Then you can geocode that in range. That the quality that you then get depends then strongly on how good is your DEM, right? So, but that's basically how the geocoding then works. And we can, because we have very good precision on the orbit, the timing information in range is very well. We can geocode SAR data very, very precisely, and we will talk about that today, that we can do that down to centimeter or decimeter level in absolute positions, which is generally much more precise than we can do optical data, mainly because we do not have so much distortions, okay? The atmosphere is not really distorting our image geometry very much. We have some delay, and we have some, in case of very strong weather effects, you may have some areas we can't really see, but the geometry is still not strongly delayed, which is then different from optical remote sensing. Okay, then we had several questions on the speckle, okay? So, which is good. That is a very difficult or very important, let's say, quite as an important point. So is it possible that the speckle also come from atmospheric effects? For example, some areas that are cloudy. And I can say no, okay, because speckle in itself is defined as the effect that comes from the having several scatterers in one resolution set. That is just a definition of the speckle noise as such. And there is, you will see like rain effects on some data, as I showed you, but it's also very, very seldom, and it's by its nature very different from speckle effect. How much will affect on real information through the speckle? Now we can get very philosophically, and I can tell you speckle is also real information. So, right. However, how much will it affect your application or your identification of a target? It can be very strong. The effect can be very strong, and it is so that we generally would say that as you should never analyze a single pixel which suffers from speckle. So you should always try to use statistics to get rid of speckle. Is it speckle effect on these images you are showing for these bridges? And yes, there is also speckle effect here. You know, probably somewhere here in these areas. Okay. Now, here on the bridges themselves, right? On the bridges themselves, there is probably, that's actually a very good question here, because if you look in some area like that, is that speckle? It's probably not, because it might be just a single strong scatter on some parts and not directly a speckle effect. So I wouldn't characterize that necessarily as speckle. And these things here, for example, this is not speckle. These are actually cars driving over the bridge, and I will come to that very soon. And what factors that affect pixel clarity and identification of objects, well, that would be number one. I would say that would be the speckle effect. So that would be the number one culprit here. Then we got several questions on the penetration. So what is the maximum depth of penetration for radar, and how effective in mineral exploration? The question is very simple for the second part. It says zero effective in mineral exploration because you're not getting anywhere very deep. So we are talking about a couple of centimeters in very dry soil, and then you have long wavelengths of L-band, probably a couple of meters in extremely dry sand. So that's not going to help you in anything in terms of mineral exploration. And typically, when you have a soil that is not very dry, you have almost no penetration. Right. So how deep can it penetrate the soil? Not very deep, and depending on the moisture. So if there is soil moisture there, we will talk you very much on the top layer. And if we talk on very dry soil, a couple of centimeter with L-band probably. And then if you have more like dry, extremely dry sand in desert areas, you can come to a couple of meters under some circumstances. Is there any standard penetration microwave lengths with various landform? No, because the amount that you can actually penetrate depends very much on the type of soil, the moisture, the wavelength. So it is very, very dependent on various factors. And did penetration depend on water content? That I can clearly answer with a yes. So it's extremely dependent on water content. That's actually basically when you reach the water, that's when your penetration stops. With the exemption of frozen water, so in ice and glacier ice, you can actually penetrate that very, very deeply. So with L-band, you can penetrate several meters, decameters even in ice. Then can we detect submarine using SAR data? That's an easy one. No, we cannot, because we cannot at all look underwater. As soon as we reach water, it's going to be reflected. Okay. So now some more sensor specific question. So what is the sensor made up? That is a good question. Right. So the very important part of the sensor is the antenna, right? Which answers also the third question. The antenna is part of the sensor. It's a very important part of the sensor, right? And then you need, you need a transmitting unit and a receiving unit, and a separation between them, and energy components. Okay. And function to really process, to really produce the microwaves and so on. So there are several elements which makes them typically larger, but much larger than an optical sensor, because nowadays you can build an optical sensor very, very small, right? The SAR sensors are much larger. We have smaller sensors with smaller antenna, but they are still, compared to optical, much larger. Also on the third question about the antennas and what's the difference between these SAR antennas and the antennas used for communication, that's a very good question, which I'm not exactly sure, I have to say. Now, because I'm not an antenna guy, right? That is electrical engineering. Now, what we use in SAR antennas typically is we use a phased array antenna, so that we can switch that we can electronically shift them. Nowadays, we typically always use phased array antennas, And I'm not so sure if we use that for communication, actually. I don't think so. I don't think we use really so much area antennas for communication. However, I have to say, well, I'm not very sure on antennas for communication. Okay, in SAR, is there only one wavelength per band, right? So that isn't, but the question in itself is a bit wrong, I would say, right? Because where we define typically the band in optical images are typically defined on the optical wavelengths. So wavelengths would be the band. However, we typically have one wavelength that we operate a satellite under. So if you would run, we can say it like this, if you have one antenna, that antenna will only work. It's difficult to build an antenna that works for two wavelengths. Let me say it like that. Okay. So typically you let run one satellite with one antenna in one wavelength. Now the upcoming NISA satellite that is operating in two wavelengths. Okay, this one will have two wavelengths, which are, however, typically in most, and I'm not exactly sure because we have to see, but they typically will be acquired separately, so not together. However, I'm not sure if they have some experimental mode where they do it together, but in the processing, in the acquisition scheme that I saw, it's typically separated. And does the signal get affected at different wavelengths, depending on the type of living or non-living surface? Now, again, I'm not sure what's a living surface or non-living surface, but the wavelengths, different wavelengths act differently with respect to different surfaces. So, for example, if a surface is seen as rough or smooth, is always seen in relation to the wavelength. So the smoothness of a surface is in relation to wavelengths, and also each wavelength acts differently to the physical objects that it interacts with. So yes, there will be even huge differences between different wavelengths. Okay, the spatial looks, that's an interesting point. Now, it is basically, the question is basically right. It is in many ways how we operate it, how we nowadays process the data, the size of the averaging window. So that is correct. However, the term in itself comes from separating the antenna, right, the synthetic antenna into different looks. So if we can process, we can say we can process the whole antenna, right, from T1 to T3, put all of that data together and have a long synthetic antenna, or we can process the data and separate it, for example, in 3 looks. So divide the synthetic antenna by 3 and get then 3 independent measurements that we then can average. So the term looks comes from this process that we can use when processing the raw data. When we process the raw data, we can separate these looks. Technically, it's also possible from the SRTM data, right? And then process them and average them separately. However, we also use the term of looks when we just talk about using a standard averaging window, right? So in that term, and it's just used as a SAR term. But the source, the true meaning of the word is separating the synthetic antenna to make several smaller antennas, synthetic antenna, which we then call looks, and we can then process separately. There is a there is a difference in that if you actually process them, because you're gonna see each look from a slightly different looking angle, which in some processing ways you can then actually take use of that. Okay. I presented the SRTM data and can explain the SRTM mission and its method for detecting the elevation on ground. Yes, I will do that. That will be part of when we go on interferometry. Okay, when we talk about interferometry, we will talk long time, okay, about how to process the data to get to a DEM with respect to all types of interferometry, and also with respect to the SRTM mission. Here, just reminding you that for the SRTM mission, we have well, the SRTM mission is a bistatic mission, so you have a receiving antenna, transmitting antenna and receiving antenna inside the shuttle, right, and a second receiving antenna here, sorry, outside of the shuttle. Now, so you can receive the signal here inside the shuttle and as well outside here, and then you can form your interferogram at one time. So both images are received at the same time, more or less. And this is ideal for creating then a DEM. You just need to make sure that there is a significant difference from the position between these two receiving antenna, and that's achieved here by this mast, where at the end of processing difficulty are then basically the vibrations of the mast, because that mast is vibrating, and you need to make sure that you correct for these small differences then here in the positioning of this outside antenna with respect to the inside antenna. We're going to talk about the interferometry and DEM with interferometry a lot, probably starting today, latest date starting next time. So next, we got some questions on the corner reflectors. Why are corner reflectors hard or expensive to make? They are not, actually. They are not expensive to make, and they're also not hard to make. You can basically, what you need, you can, if you position it correctly, you just need a metallic plate, right, or a conducting plate, and orient it toward the sensor. It would be a mirror and a simple corner. You just need two metallic plates at a perpendicular, right, at a right angle, set them up. That's not difficult to do, right? Also a corner cube where you then put three plates together. It's not difficult, okay? It's also not very expensive. You could basically use very cheap metal, scrap metal at the end to do that. If you are using your corner reflector to calibrate your satellite, okay, if you use that and you want to measure the backscattering strength of the corner reflector, and you want to do that to calibrate, that's going to be expensive, right? Because then you need special steel. Then you need steel that does not expand very much in heat, okay, and does that keep the similar area under certain weather conditions, need to be stable and relatively large, and that can make that rather expensive. But that is for calibration use, typically used for people, space agencies who run the satellite, right? And then, you know, compared to the cost of the satellite, it's still relatively cheap. Okay. Now about I showed you the example of the corner reflector, which actually was not filled with water, just sprayed some water on top of it. Is it double bounce? And That's a good question, right? So it's in 3D. I hope I can paint it. So if you have such a dihedral, right, you hit here, you hit this wall, and then you go back. This is double bounce effect. Okay. But that one was a corner cube. In a corner cube, it is typically a triple bounce. So you typically you hit somewhere here, you reflect here, you hit that orange wall that gets reflected to the other side wall and then goes back. So in the corner cubes, we often find that we actually have triple bounce effects. It's rather, in that case, it was rather a triple bounce than a double bounce. Okay. How SAR work in desert? I have to say, I'm not really understanding the question because it's as such working the same as well in a desert. So it's working actually even better in a sense, because for many applications, the whole vegetation and objects that move around, that's actually what disturbs many effects, especially when you talk interferometry, which works typically much better in desert areas. Where we can download free L-band SAR data, I do not know. I can tell you. I don't know a free L-band data source at this time. You can download free C-band data and L-band data. You can try to get from JAXA, from the Japanese aerospace agency. They run L-band data, and the older ALOS PALSAR data is maybe available for free or after a registration process. I'm not sure. Right. I know where you can get easily get free C-band data. So how we are able to identify the single, double bounce, triple bounce from the images of Wuhan? Is it speckle effect on these images? I got this question before. Okay, is this also raw data or process data? So let's take a look at that. Okay, first on how we know which bounce it is. So we just know that from in that case, from the timing. Okay, so if you have such a bridge, the single bounce data, right, that will be the shortest path, takes the shortest time because we hit the bridge and directly go back. It's the shortest distance to the sensor. That's to say that will be the data that appears most close to the sensor in the SAR image. Now the double bounce data takes longer. It's a longer path because it hits the bridge and then goes down to the water and then back to the sensor, which is a longer path, takes longer for the signal to come back to the sensor, so it appears behind the sensor, right? And the triple bounce takes even longer, right? It hits the water, hits under the bridge, goes back to the water, and comes back to the sensor. That is even a longer path, so it appears behind the double bounce. That's how we know it, just as we know the path length, and we can get the geometry of it. It's based on the geometry of the signal of the data. So again, here then we can see the single bounce, and we identify that this is single bounce just by the timing. Right? The looking direction is here, so this one is closer to the sensor than the double bounce lines here, right? And the triple bounce behind there is even more far away from the sensor. So we get this from the geometry of the data, we can infer that. Okay. Now, can we identify from SAR image about single and double bounds and this build-up area, double bounds or volumetric bounds? So we have just now I said, well, we can, in case of the bridge, we can infer that from just the geometry, right? But that's not the only way to do that. The other way is if we have a polarized data, if we have polarization data available, full polarization, we can separate the number of bounds or the type of bouncing by analyzing the polarimetric data. For example, as one way with the Pauli matrix, where we see if we add the HH and the VV up, that will be very strong backscattering then of strong band if you want. For single bounds, double bounds would be stronger if we subtract HH minus VV, then that typically highlights the double bounds effects because they're stronger in HH. So in that way we can highlight them. And volume scattering is strongest in this cross scattering in HV or VH. And there are other ways to decompose these polarization matrices and to analyze the number of bounds is the physical, what's physically happening with the data, with the wave on the wave. But to do that, you're gonna need the polarization information, ideally the full polarization, all 4 polarizations. Although if you only have 2 polarizations, you can also start to infer some of the information. But ideally, if you have all 4 polarizations, by analyzing the full polarization matrix, you can infer the number of bounces. Right, and here, in that simple case, is the Pauli matrix. You can then see the single bounce is here more bluish, and then the volume scattering is green in the image here, and the double bounces are more red. And so you see that we find more double bouncing in the urban areas. So the urban areas, in that sense, they are, if you have buildings, right, and roads and urban structures, they are not volume scattering, they are double bouncing, right? If you go very deep in polarization, and we will not really do that, but if you go deeper in polarization, you will find that you can see also this cross polarization at buildings, because when the building is not in 90-degree toward your sensor, the tilt of the building can also shift the phase and the polarization of the phase, so that you may see also HV or VH polarization being relatively strong in urban areas. However, it's still not volume scattering then. Then it's just a misinterpretation of that polarization as volume scattering. There is no volume scattering at buildings in that sense. Okay, so, right, that was it in terms of the questions. So keep on asking, and I'll try to answer them as good as I can. If I did not answer you, if you're not satisfied with my answer, try to rephrase them and pin me down and see, what is it exactly, that you want. Maybe rephrase it if you think I did not answer you or answer you not correctly. Okay. Now let's talk a bit about where we stopped last time with the SAR interpretation, and we move on to some more strange effect, some artifacts and ghosts. And we didn't really mention that yet. I just showed you on the bridge in Wuhan, and I said these are cars, but I didn't explain it. And now let's do that a bit. So when we have an object that is moving in the SAR image, moving fast, like a car, okay, that can, that's disturbing the imaging process, okay. So if you remember, when we take our SAR image, we are taking several images along the path that we combine, or if you think it, if we explain it with the Doppler effect, we identify along the path, we are moving towards the object, now we are next to the object, now we're moving away from the object using the Doppler effect. However, if that object that we are looking is moving by itself, that Doppler effect is distorted, okay? So if I'm looking at a moving car, my Doppler effect, when I think I'm next to the car, is actually wrong, because the car and the motion of the car by itself creates also a Doppler shift, okay? So I'm misinterpreting that. And what then happens if you have moving cars that move toward the sensor? In this case, in these two images, the looking direction is actually here. They're looking from top down. The cars are moving over the bridge, mostly toward the sensor or away from the sensor. In that case, they are positioned wrongly in range direction, and they are more away in range direction the faster they are. The faster they are, the more they are shifted. So you actually can even measure the speed of these objects. And if they move in this direction, if they move together with the sensor, they get smeared. So they are not sharp anymore in the SAR image, which you also see here. For example, there's some smearing inside. It's distorted and smeared because that bridge, well, is moving, the cars are moving toward the sensor and a bit to the side of it. So we have here a shift and a smear effect for these cars. And that's true for all moving objects. We see them here very clearly because we have a bridge over water. So we see these cars because of the strong contrast to the water. However, this is true for all moving cars. They are all misplaced, and there might be misplaced cars somewhere here inside, right? Or somewhere here also. In this case, we can't really recognize them, right? But this is an effect for all moving objects. And here is similarly what we see here actually is a train. It's a train that is displaced, and the train is missing here, right? Where you can see that black area here. That's actually where the train should be, right? That's the area where the train should be. Now the train is missing because he's here shifted due to the, well, it's an effect of a SAR image. So the displacement due to the motion of that object by itself. The object moves by itself, the Doppler is shifted. Now, in most cases, well, that's just an annoyance, okay? So it's you can call it a kind of an error if you want, but we can also use that. So we can use that to identify cars crossing a bridge. You can use that by just counting here that cars, identifying them, counting them, separating them from ships. That's possible. It's not great. It's not very useful, right? Because you can only do that when you have a black background. However, if you build your SAR system a little bit differently, if you orient your antennas differently, you can identify directly all moving objects in the scene, and can then you have a moving target indication, and you can build a SAR system that directly maps all moving targets with their speed and their position for a rather large area. And that is very much done for airborne systems, especially in the military context. So where you then have the ability to track all moving cars, all moving objects for a rather large area. and that works very, very well. You will not find a lot of publication on that field. That's mostly because that is typically used here by security and for military application. But you can do that very, very well. But you need to acquire the data a little bit different. There is also experimental data available where you can do that and play with that. But in normal data and normal acquisition, it's not so easy to do, and you cannot do it such good as if you switch to a long track interferometry. Okay, but typically for us, we see them as distortions. Okay. Another effect here, that's some ghosts here. Now this is that's Barcelona airport, and when I first looked at the image, I was thinking that is maybe some weird effect from the maybe some interference from the radar on the ground, or some ground interference. I didn't really know what's that, to be honest. However, when we looked more longer and more closely at the scene, we can identify the true source of that problem. And that is actually that area here. So here we see some build-up area that reflects very, very strongly for reasons that I do not know. Right? These buildings, they're probably just oriented directly to 90 degree toward the sensor or something like that. But in any way, they reflect very strongly. And what we see here is just a ghost signal from this one here away, actually in the footprint size of the sensor. So you can see them here, but they are just a ghost signal of this area here. And when we zoom out even more, we can then identify them being here, the ghost, and we can identify a similar ghost then the same distance around here. Here we just don't see it so good because now it's together with a signal from build-up area, right? And we can also find them around here in the water. We can also see them, and the other ones, they would be outside of the image actually, so we don't see them. So this is just a ghost effect from this very strong signal here. Now, how do I say? After we identify that, right, we can say, yeah, okay, this is just some SAR effect, okay. But this can this is the source area where it comes from, but it can be very annoying, right? If you think about it, if you write some application, if you write some tool, if you work on target detection or classification, right? Well, in the case of the airport, right, we could probably, because it's very obvious here that this is some strange effect. Well, your target detection is now messed up, but at least you can kind of explain what's happening, or just shrug and say, well, that's a really strange image, okay? But if you analyze your image, you would at least see there's something strange going on here, even if you cannot explain it, right? But again, if we go in here, and you would classify something in that urban area up there, right? Let me get that pen here, up here somewhere, right? Yeah, you probably not know why your classification is wrong there, right? It's the problem is this ghosts that if you can identify them and you think a long time about it, it gets clear. But you know, if you do some classification process, and you just get then a bad result there, you would probably not know why. So this is something that can be really, really yeah, annoying. Okay. Okay, this is the source of them. We don't really know why. Yeah, but you see they're like 90 degree toward the sensor, and probably even their roof is probably just we hit them probably here at the right angle or something. As I said, we're not sure why these buildings reflect so strongly. Okay, so ghosts, they're strange. Okay, and the moving objects, and we have some strange effects. Okay, but nevertheless, okay, we still want to interpret these images, and a typical application for that, where we very often rely on SAR data, is post-disaster damage assessment. So we want to see after disaster, what's the damage, okay? And we want to see that fast, right? So if you work toward damage assessment, post-disaster damage assessment, you want the images very, very fast, okay? So you can't wait, not even a day, right? Typically, we talk on hours as soon as you can get the images. And here's often then SAR being used because of the all-weather capability, right? And you can rather flexible point them, but especially all-weather capability comes here because, well, if you have an earthquake and you have clouds over it, then your optical satellites can't help you much, right? Then you must use SAR, even if the images are full of speckle, okay, and even if you have ghosts and the geometry is messed up, right? You still have to use it because there's no other data source available. And similar for flood, even worse for flood, because very often floods are related to rainfall, well, and clouds bring rain, so it is very common that you have that the scenes are cloudy during a flood event, right? That is the common case. So that's why, again, there then SAR is very often used because we can get the images fast under almost all weather conditions. So post-disaster damage assessment is an important field. And I will use one example here from the Wenchuan earthquake here in the town of Beichuan, which was, as you can see here from these optical images, more or less completely destroyed by landslides that have been triggered from the earthquake. So most of the damage, we see some collapsed buildings due to the earthquake, but most of the damage has been done by landslides that have been triggered by the earthquake. So let's take a look how that looks in optical image versus a high resolution optical image, and you can see the bridge here has been damaged here on that side. Okay, and that part of the bridge is totally collapsed. We see also some building damages, but next slide we are focusing on the situation of the bridge. Right, and also in the SAR image we can identify that. Right, we can identify the damaged part of the bridge here, right, and we can also identify the collapsed part of the bridge. But right, you can identify that if you're not really used to SAR images, you can identify that because I make big pointers there, right, and point you to it. But I think we can all agree that the interpretation is much more difficult than optical image. Right? That is just the fact that is due to speckle, but also mostly due to the different geometry and the fact that it's a very different wavelengths from what we are used to with our eyes. So, you know, optical images are interpreted very naturally by us, while SAR images we actually have to learn. We can interpret the damaged part of the bridge, mostly because of the missing part of the shadow from the bridge. Okay, we can see that here. That something is up here with the bridge, and collapsed part of the bridge, it's a bit different. We can see that, well, what we see down here is actually, the collapse, that's are the bridge parts in the valley that are now down there. We can actually identify them. And otherwise we would see that it's a collapsed part of the bridge, basically because of the, well, the shadow is not straight anymore, right? That is just, that just looks wrong. People who doing that professionally, they train a rather long time on that. Okay, SAR image interpretation, assistant optical image interpretation is something that is then trained and takes a considerable amount of time. Okay, so here I just go through that a bit. All right, okay. So would you mind mute your microphone? Right, okay. Good. So here we have now, it's a bit complicated, that part. Try to follow me because we will. It's not so easy to understand from the images. You have to try to remember this image here so that you know what I'm talking about. But we will see then different effects of SAR images. So what we see, we just looked at A and B. That's just a bridge that we just saw. We have area C. That's the landslide that comes down here. We have area D. That's another landslide that came down here in the town, very destructive one. We have then area E, which has also been destroyed by a landslide coming down here. And we have MR, which is Mountain Ridge 1, Mountain Ridge 2, and Mountain Ridge 3, which is basically here the ridges of the mountain. You saw it in the pictures, these mountains. They're very, very steep. It's going down here at Beach Run. It's going down very steep down the mountains. So the layover effect and foreshortening effect, as you will see in the next SAR images, is very, very strong. Okay, so try a bit to remember the situation from the optical images, because it's going to look very different from the SAR image. Okay, so we have two images here, ascending and descending image. This side is descending image, one side is the ascending image. So we're looking from different sides at it. All right, and when we're looking, right, so A and B, the bridges we can see from both sides, we can identify them. But if we talk about landslide C here, right, we can identify that landslide in the ascending image, but we cannot identify it in the descending image. It would be, well, it would be somewhere here, not so sure, right? The reason is that in the descending image, the landslide C is in the layover. So we can't really see that. What we see here is actually the landslide on the other side of the ridge, going to the left, so going down here. That's the landslide that we see in that image. So we see, we see that side here, right? That's what we see here, but not a landslide C. Okay, now the opposite, but the same situation is a landslide D, which we see in the descending image, right? We see it here, but we cannot identify it in the ascending image because it's under the layover. Okay, so if you only look at the ascending image, if you do not have the descending image, you wouldn't even see that very, very destructive and very deadly landslide here, which I marked D. It's not visible, right? It's in the layover. Now area E we see in both images. Okay. Again, the destruction caused here, we can identify much better in the descending image because we see here, we see the line to the buildings. Okay, we see here are the buildings, that's how they should look like. Right, and here something happened in this area E. Now we see the destruction also in the ascending image, but we do not see these normal buildings there under the layover. So without additional information, that is much more difficult to identify. Right. So what you should learn from here is the interpretation of the images can be very difficult, especially in such a mountainous area as we have here in Beichuan, right? Because of the layover effect, foreshortening effect, and shadowing. Right, ideally, under such circumstances, you have ascending and descending images and interpret them together. That can be very, very helpful in that situation, right? We also see that it's much more easy to interpret and identify damages from optical images. Much more difficult here from the SAR image. It's possible if you know what you're doing, but it's not easy. Okay, and due to the geometry, and this extreme case, we need we need both ascending and descending images, which makes the whole process more slow because you need to wait until you get 2 images to really see the full damage. You also saw the layover effect in action, right? And hopefully helps you to understand a bit more on the layover. Right, this is area E. This is the last building standing is an overstatement. It's also not really standing anymore. Right, and this area here, you also see very strong destruction here. We see here can basically identify that last standing building by its shadowing at number 1. We can see some of the destruction here at 2. And we can identify better the image on the lower right side. That's a higher resolution image. It's a spotlight image, which then is very helpful to see. But the destruction in that area is so strong that we cannot identify much anymore. Okay, it's all basically down to chaos, and we cannot identify any linear structures or something which we normally do to identify buildings or, well, anything. Right? It's really down to almost to noise, to pure entropy in that destruction, in this destroyed area here. Okay, now come to another example. The same earthquake, another application that was at Tangxia Mountain, Tangxiashan, where we have, you see, we mark that if you can read Chinese, you see Beichuan, that's the city that we just talked about. That is here. That's the destroyed part of the town that we just talked about. And we had also a huge landslide here at Tangxiashan. That landslide actually blocked the river above Beichuan. You can also see that in the images taken from Beichuan because there's very less water in the river. That river was blocked by a landslide here that then blocked the river so that no water came upstream, and we had then such a dam blockage lake being created upstream, right? And that was very, very dangerous. That was after the earthquake a very dangerous situation, because if the water gets above that landslide, above the blockage, that natural dam, that landslide dam, will break down at once. Okay, and the whole water goes downstream, and you have then huge danger of extreme flooding event going downstream. So there have been hundreds of thousands of lives being in danger, actually, if that would happen. What was then done was actually there was then a channel has been digged here by the local forces and by the helpers that then let the water out in a controlled manner. Okay, but that was a race against time. And it was very, very important to always monitor the status of the water behind the dam. How high is it? And when was it too late? When do we need to evacuate, right? When do we send the alarm? When the workers have to stop? When we have to evacuate people downstream? So that's a very, very important application, which has been done by all kinds of sensors, okay? But SAR was one of them. But there was also many airplanes. At the time, there were not so many UAVs, more airplanes, but basically every sensor that you can think of. That's the landslide, actually, that caused that blockage, which, to the best of my knowledge, has actually also been identified in that SAR image that I show here. And that here is the scar of the landslide, and that here is the accumulation of it that actually then caused the river to being blocked, right? Again, we can see that landslide here in ice. One is the ascending image, one is the descending image. I'm just looking, but it's not really written which one is which. But again, we can identify the landslide in one image here. This is the car, right? But in the other image, again, we wouldn't see that landslide because it's in the layover. So again, if the layover is so strong, sometimes you cannot see anything anymore. It's a similar situation as before, but here we want to talk about the water. So this is the normal situation upstream. It's several years before the earthquake. That's 2 days after the earthquake. You see the water is starting to get larger here, and then more than a week, almost 2 weeks after the earthquake, you see that's at the highest status of that dam lake. You see it's a huge lake has been built here upstream. And we can also do, and it also has been done here with lots of SAR images. Here is an image taking 2 days after the earthquake. Another one 2 days later. You see the lake is growing here, right? And we can identify water relatively easy, right? As long as it's calm water, which in a lake it typically is, by identifying it as black. However, in an area like that, you would need to make sure that you not confuse the shadow of a mountain with the water. So you would, probably need to take a DM or something into consideration. But in that post-disaster damage assessment here, this SAR data and these images here, they have been used operationally for that. And it's one of the first time to do that with high resolution SAR data, because the image is from 2008. And that was one of the first huge disaster where lots of TerraSAR X and Cosmos camera data, which just have been launched before that, have then been used, showing here the usefulness of high resolution SAR data for these purposes. Another example of how we can use that here is again looking at bridges, and then we look at bridges here downstream of the dam lake, and we can use here analyzing the geometry between the single bounce, double bounce, and triple bounce to see the height of the water level. And how are we going to do that? So let's take here the extreme image. That's May 22. That's when the water level was the lowest because it's down of that dam. downstream of the dam, so the water has stopped basically, and the water level of that river get lower and lower. And with a very low water level, you have a very large distance between the bridge and the water. Okay, that if that distance gets higher, your single bounce gets more far away from your double bounce, and again more far away from your triple bounce. So the distance between single bounce, double bounce, and triple bounce gets larger when the distance to the water is larger. And so you can see the distance. Here's the normal case. June 6 is again back to normal, the water level. But you can see May 15, May 22, how the distance between the single bounce, double bounce, and triple bounce of the bridge gets larger. And we can use that to calculate actually the height of a bridge over water. It's rather simple. You take the range from the double bounce scattering, right? Subtract it from the single bounce scattering divided by the cosinus of the incidence angle, and you get the height of a bridge over water. Similarly, you could use it from triple bounce to double bounce, because the distance between single bounce and double bounce and triple bounce and double bounce is identical. Okay. So with that very simple formula, you can just by hand calculate the height of the bridge over water. And in cases, applications like that, you can very simply therefore estimate water level of the river. If you know the height of a bridge, then you can get the water level of the river, the changing water level of the river very quickly, and also very easily. Okay, which in this case of post-disaster damage assessment is very important, that you have some easy solutions, okay, where people just can go and do it, okay, and not have the most sophisticated approach. All right, okay. So that was on image interpretation and how we create SAR images. And now we are gonna move toward creating digital elevation models and surface motion, which we are now basically focusing for the rest of the lecture on. And then this is where SAR really shines. It is a very important tool for something like the damage assessment, disaster monitoring, because of its all-weather capability. But true strength that we can see is in digital elevation models and surface motion. That's also what you can say. Basically, that's also where the money is made. If we take away military application and security applications, then digital elevation models and surface motion estimation is basically the money maker. Now, we will first talk on amplitude-based methods. These are methods that are not looking at the phase, but that are looking at the image that we just also looked at, a typical SAR image, the amplitude of the image. We can also get DEM and surface motion by these methods. It has some advantages compared to phase-based methods. Both of them can be used. And honestly, I never know which one to teach you first, okay? Because now we start with amplitude-based methods, but then we compare them to interferometric methods, which we didn't discuss yet, right? However, if I do it the other way around, I have the same problem, because all these things, they connect and belong together. So I'm just starting with them because we are at the moment still on amplitude images. All right. So if you use SAR for DEM generation, we have several advantages. We have weather and illumination independent, which leads us to fast data acquisition, right? fast data acquisition is because we are weather independent. So we get the data under clouds, and therefore we can acquire them faster. And we can achieve with interferometric SAR, when we use phase-based approaches, we can achieve very high precision, better than with these amplitude-based methods that I show you now. So we have different methods for amplitude. We have different methods at all for creating a DEM from SAR. One is stereo radiogrammetry. That is very similar to photogrammetry. Okay, we use two images taken at different angles and then generate a DEM by analyzing basically the differences in the geometric shift. Right. We have then interferometric SAR, which we will talk most about, but probably starting next time. But we will spend most time on that one. It's the typically used method. It gives us the highest quality of the data. Then we have a SAR clinometry, where we just look at the amplitude changes. We can also reconstruct the DEM like that. That is basically shape by shading, right? Which we also use for optical shape from shading. That would be in SAR clinometry. And you can create a DEM from polarimetry by analyzing the polarimetric shifts that are caused from slopes, which we will not look in here, I think. Okay. Anyway, SAR clinometry, we are looking at, for example, we are looking at the radar shadow, the length of the radar shadow. We can use that to measure then the height of an object. If we measure the shadow length and use trigonometry, we can calculate the height. It's a very simple approach to do that. Also, we can look at the amplitude, and if where's my little pen, right? If we have an area that looks toward the sensor, that will be more bright. An area that looks away from the sensor, you see that here is the area looking toward the sensor. Looking away from the sensor is more dark. Now, if we say, well, all of the surface, they reflect the same. We assume they are constant and diffuse reflection. We can use that. That would be, and we can calculate the reflection, and then we can get the normal vector of that in comparison to the sensor. So basically, we can get the slope from that, and then we can reconstruct the DEM. But that's under the assumption that all the reflection is constant and diffuse, which is, very seldom true, right? Just say, well, it's everywhere the same reflection. It's not so, it's not really realistic. But the method was used for mapping Venus, for example. Okay, that was used for getting a DEM from Venus by saying, well, honestly, we don't know if there is always a constant and diffuse reflection on Venus, but it's all we got. Okay, it's just, we have nothing else to go on. And you get, a relatively suitable DEM out of that. Okay, and so the method was used on Venus. You could also use it if you have, for example, a tropical rainforest, that coverage of that tropical rainforest is very smooth in a SAR image and very constant. And in these areas, clinometry would also work rather well. However, it's not a very widespread method because we have better ways of doing that. Okay. A more widespread method is radiogrammetry. So we take image from two different angles, okay, and we then analyze the difference of the shift in range direction. So the layover is different, the shift is different depending on your incidence angle. So if you have two different incidence angles, you look of how much is the layover, how much is the pixel shifting. You can recalculate the height out of that, right? The difficult part of doing that is just finding the same object, the same points in both images. It's very similar to photogrammetry. So you need to find the homologous points, which shows the same object, the same point in image A and image B. Okay, if you can do that, then you can calculate the height rather simple using that equation below. That's the only strange thing in that equation is here. There's a plus or minus. It's either plus or minus, and that depends on your formation. If both images look from the same side, or if you look from two different sides. Do I have that? Yeah. So on the same side configuration, so we look from the same side, but with two different angles here. That's the option 1 that we have right here, same side. And the other one is the opposite side configuration. We look at the same object from opposite sides, right? So the opposite side configuration will give you more accurate results. Okay, it's the better geometry. However, it's much more difficult to find similar points in the opposite side configuration, right? There's also, you see, that whole mountainside here, you don't even see from the other side. You don't even see that, okay? You couldn't find any point there, right? So it's the much more uncommon approach because it's very, very difficult and sometimes impossible to find the identical points in both images from the opposite side configuration. So this configuration, the same side configuration, is the normal case. However, theoretically, the opposite side configuration would give you better results. It's a better geometry, but it's so much more difficult to find the same identical homologous points that it's typically not even working. So wait, direction this one here. So if you have here two images taken at different sides, what you need to do is to find these similar points. So that point is here, right? That point is here in the other image. That point is here in that image, and here in that image. You need to do that for ideally all points that you can find. And if you identify them correctly with a good precision, ideally with subpixel precision, then you can calculate the height and the height differences between 2 points, and then you can get a DM out of it, or actually a DSM out of that. That's how it works. It is it's not a very difficult process. The only really difficult part is to find these identical points all over the image. It's easy for some edges, okay, along a road or something. It's relatively easy, but all over the image, it's actually not so easy to do that. There are then different methods to do that and to find that. Many are based on photogrammetry or similar to photogrammetry in its approach. I have to close that one again. Okay. All right. So we co-register the two images to create then an epipolar image. We can use a low resolution DM, for example, to assist with that, right? So we can co-register them better if we have already a DM from the area. But it's not a must. It's not must have. You can do that, right? Then we find the range shifts for each point, and then we can calculate the relative height or height difference between 2 pixels. And then we can get the DSM finally in world coordinates. So it's a rather straightforward process. Again, the difficulty lies in the step of finding the similar points. Here's an example from Malaysia. 2009 is a rather old example, but not uncommon. Because why Malaysia? Because due to the forest there it's sometimes very difficult to process the area with interferometry, which you will understand after we talk about interferometry. Just believe me now, okay? In that case, then sometimes we prefer radiogrammetry, sorry, because that also works under these circumstances. Radiogrammetry is more stable. It typically works in much more cases, right? We get them, actually, I just want you to show you that one so that you understand a bit. What we get out of it is typically something like that with a lot of void areas and holes in the DSM, right? That's what we get out of the processing. So if you do not find enough points, some points are in the shadow, you can't do that. That's what comes out of the processing. And if you see a final result like here on the right side, right, where these voids, they have been removed by post-processing, okay, either by mean imaging or something, by masking them out, or I think in that case, even a lot of manual reconstruction where people actually click that points, right? So don't get, I show you that, just don't get fooled. That's like the left side, that's how it actually looks like if you process it, that's normal. The beautiful result on the right side, that has been altered. Somebody put some work on that to get from the left side to the right side, right? So just that you are aware of that. If you ever do that, that's how it looks. That's actually, left side is already a very good result, right? And then it's very common to get these voids. That's then post-processing. Also in interferometry, when we go over there, such void areas are very, very common. Okay, advantages and disadvantages. It's very stable and almost weather independent. It just uses the amplitude, does not use the phase, like we talk about later, which makes it more stable. And it's very comparable to photogrammetry. So it's kind of, you can use a standard processing scheme, right? However, the accuracy that you can achieve depends on the spatial resolution of a sensor. So if you have a sensor with a high spatial resolution, you can get a better accuracy. That's very logical, right? However, that's not the same in interferometry. That's a difference. So that's why I said, if I teach this first or that first, there's always these connections are now missing for you. Okay, I hope at the end we get it. Okay, because in interferometry, the accuracy does depend on the wavelengths and not on the spatial resolution of the sensor. So that's why this one matters here. I have another example here from where we processed that at Mount Sung in China. It's a funny example. It's a funny example because it's another one with bad weather, right? So we have one image where we get a good image, and we have the second image where we also had some rainstorm here, right? With some rain event and shadow. Okay, and if that would be, if you would try to process that with interferometry, we can basically say that wouldn't work. That weather would mess us up in many ways. However, with stereo radiogrammetry, we still can process the data. However, clearly in this area here where we have the rainstorm, yeah, there it won't work. Okay, but the rest of the image is still working, which is a bit different. I believe in INSA we will not get any results here. And that's how we can get here result here. And that is the right side, you see the correlation, the maximum correlation that we achieved. And then you can see here in the rainy area, we do not achieve a good correlation between them. Well, because one image has rain and the other doesn't. So they do not correlate well. Right? But over large other parts of the image, we get good correlation. There we have some shadow areas, some layover areas, where you also cannot correlate these two images so well. Right. Okay. Now, I don't want to talk too much about stereo radiogrammetry because you're not really using that very much here. But it's important to see that we can also use the amplitude. And similar, we will talk a lot of time on measuring landslides and motion with phase, with interferometry. But amplitude also have ways with pixel tracking and point target offset tracking. This is also an approach to do that. So in offset tracking, what we are doing is also rather simple to understand. Okay, so what we typically do, we have one reference point. Okay, so let's say the black one is a reference point where we say, okay, this point is stable. Right now we're looking at motion actually. So pixel tracking, target offset tracking is looking at motion. Okay, so we say that black object, that pixel is stable, it's not moving because we think so, or because we know so. Maybe we have some additional information, or this is, it's not on the side of a mountain, it's a very stable point. Right? And so we identify one point that is stable. Okay, and then we look at other points, for example, the gray point. And we just look at the distance, right, between the black point to the gray point. Is that distance changing from one image to the next? Okay, and in that way, we can identify motion. Again, the difficulty lies into identifying the stable point, finding the same point in both images. For the point we think is stable, and for the moving points, we have to be able to find both points in both images, and ideally we need to find them in sub-pixel precision so that we get, measure the motion very, very, very good. Okay. So, but in principle, it's rather simple. We identify a fixed point, and then we just look at the distance differences in two images between them. Right, and then we use, we can use different approaches, right? But typically we use normalized cross correlation to match them and identify them, and then see how that changes and where is the exact fit between these two images. We can get there in a relative good accuracy. So if we have, a coherent correlation in that case of 0.6, right, and a window size of 32, we can get around 0.1 pixel. If you have very good correlation, we can even go to 0.05 pixel. But like a tenth of a pixel, 0.2 of a pixel is something that can realistically be achieved with that method. Okay, if we can find good enough window sizes and match them well. So something in the accuracy, with the motion in the range of 0.1 of a pixel or higher, that's something that is realistically measurable, right? 0.05 pixel under very good circumstances, but 0.1 as a rule of thumb, that can work, right? Now, again, or not again, because we didn't really talk that yet, but we're gonna do similar things in interferometry. The pixel target or pixel offset tracking is suffering from speckle. Okay, and lots of the loss of accuracy are actually caused on speckle, and you see we need larger window sizes to get rid of that. However, if you find point targets, and point targets can be these artificial targets or naturally strong scatterers, and we find point targets that are very strong and that dominate the scattering in one pixel, that we say, if we have such a corner cube here in that pixel, that corner cube, the backscattering from the corner cube will be so strong that nothing else in that pixel matters anymore. It is dominating that. In that case, we don't have speckle. Okay, in that case, we don't have speckle effect. If we don't have speckle effect, we can get even better, higher accuracy. And in the case of point targets, right, it depends on the signal to cluster ratio of the point target. If that one is very high, if you have a very strong target to a weak background, right, we can get accuracies much better than 0.1 pixel, even better than 0.05 pixel with very bright, very strong targets. Right? And if we have those targets, you see, we can reach very good accuracies and then compare the motion of these point targets to each other. What we need to do that though are these point targets, and right, we will come to that. That this is not. They are not well. They are not often just not available. Right, so that is the main problem. But if we have such targets, or if we install them by ourselves, then we can reach very good accuracy here. Now, let me see. Okay, all right. Now we come to a different topic, which is the SAR Geodesy. Okay. What is SAR Geodesy? Right? I don't have a slide for that. Let me talk about it. So on the SAR Geodesy, in that case here, we understand the precise measurement of also point targets in absolute world coordinates. So we want to identify the precise position of such targets in world coordinate system, so the 3D positioning of these targets. And there is work going on that, and because we have very good satellite orbits now, so we can achieve positioning of such targets in absolute, in decimeter or centimeter accuracy nowadays, which is very, very good and very difficult to do even with GPS in absolute coordinates. So we tried that. We tested it as well. We set up some corner reflectors here on top of one of our buildings here. 2015 is some years ago. Also, we set some up in front of the entrance of our university. And we did some very first experiments here. And we just did not really correct very much. And we achieved very good positioning already in azimuth, where we were up to about 2 centimeter precise. And in range direction, that's the direction the satellite, the signal is traveling, we were off by about 1.6 meter. So that's rather long, rather big difference. However, one has to say we are very good in azimuth, but maybe we just got lucky. The 2 centimeters seemed a bit too good, right? It's more likely that it's more about 5 centimeter that you can achieve easily with Teresa X. Now, why 1.6 meter? The most reason for that is that a signal going through the atmosphere is actually not traveling the speed of light. So we assumed speed of light, but that's not true, right? The signal is slowed down going through the atmosphere, right? So we have an error of 1 meter, 2 meter, which we call the tri-atmosphere, which is rather constant going through the ionosphere and the troposphere. And then we have 20, 40 centimeter error, which is caused by differences in the humidity, the air pressure, and so on, which is dynamically changing in the atmosphere. So we tried to correct for some of them. Okay, so we set up a second experiment, a little bit more. A little bit better, actually, a bit better experimental design as well. We corrected for some of the delay, and we got here down to some decimeter accuracy, more or less. Still good in northing, which is basically the azimuth direction, and eastern height is basically the range direction. However, there's still problems there. So we have to consider the dynamic Earth. We have our Earth is constantly moving, right? We have nothing is actually really fixed. And for example, our reference frames, they are typically set to a certain date. If we do not correct for that, so now in Europe, we often refer to what's it called, ECMF, anyway, from 89. So that is now 30 years old. If we assume the Eurasian place is moving 2 centimeters per year, that's easily 60 centimeters off now in absolute coordinates. If we do not correct for that, right? If you are from Geodesy and you know what you're doing, right, easily to be corrected, okay? But one has also to be aware of that, okay? So this is one thing. The other thing are, for example, solid earth tides. So the earth, you know, tides from the ocean, but the earth is also lifting and shifting following the moon and other stellar objects, mostly the moon, right? And that can be, that is about 30 centimeters a day, up and down in general. So again, if we are looking for absolute positioning, and if we are trying to reach accuracies better than decimeter, centimeter level, we have to correct for that, okay? Now again, the solid earth tides, you can download the information and you know the time when the images have been acquired. So you can correct for it. Again, it's more problem of being aware of it. After we did that, also including the solid earth tides, we went down in most cases to a couple of decimeters being off, and that is now mostly related, the rest is mostly related to the atmosphere, to the dynamic part of the atmosphere, which is the water vapor content, the air pressure, mostly these, which affect the path delay of our signal traveling through the atmosphere. Also, we can try to correct for that. There are atmospheric models available. You can get the atmospheric, the numerical weather models who include all these parameters. However, the main problem is that the resolution of these models is not very high. Okay, so you have to interpolate them, and that works well if you have relatively stable weather condition, right? So the interpolation of them, if you have relatively stable, smooth changes in the weather condition, you can also interpolate well. However, if you have a very dynamic weather situation, with a very bad resolution, a very coarse resolution, the interpolation will not work very, very good for you. Okay, so that's the problem of them. At the end, it's then a problem of like correcting that and interpolating well in these weather models. If we do that, in that case, down with descending data, you see we can reach here actually the centimeter accuracy that we were aiming for after correcting for the weather model here in absolute parameters. Now, interesting is we need these high, we need these high SCR points. And if we take a look in Wuhan, how many of high points we can find, naturally, you see we can find rather large amount of points, at least in one image, if you want to find them. Similarly, in all 4 directions, it's getting a bit less. If we do that, then we can identify them and we can get their exact precise position and height over ground based on this SAR geodetical approach. And the DLR, actually, they are much better at this than we are. I have to say, we played around with that a bit. They have a whole team working on that. And what you can achieve, you see, is around 6. Now they're down, actually. They actually got better again. But let's say better than 5 centimeter is what you can achieve in that, in the positioning of these objects. And that is a very, very strong and very useful tool. Now, why is that useful, right? And it takes a bit time. Many people do not immediately get why that is a very useful and extremely valuable product. So what it allows you to do is you can have ground control point free absolute positioning of targets in centimeter or decimeter precision. So you get these point targets here, absolute position in centimeter, let's say decimeter, without going to the ground control point free. And that has actually been used in the production of the World DEM, of the Tandem DEM. They have used this technique to get the ground control points. In that case, it's actually not really a ground control point anymore, right? Because nobody have been at the ground to get these control points, where then the DM is anchored on. They have been produced from the SAR data by the methods I just described. But you can also buy those. It's a product sold by Airbus. You can buy those ground control points. And if you buy them just as ground control points, they give you the points and a small map, basically, where you can then connect them together. But who is doing that? Who is buying that? And that's actually, well, there is a large interest in the security-related, right, military-related, security-related, because if you have these ground control points, let's say from a country you can't go, so it's very interesting to get very good, high-quality ground control points of North Korea, for example, right? So now you have your good ground control points in centimeter accuracy of North Korea, and now you can use them if you manage to match them to optical image, right? If you have them, you can link your SAR image, your ground control point detected in SAR with an optical image. Now you can automatically correct large number of optical images, and now they're able to have ground control point free and fully automated mapping, right? So basically, we are moving toward the goal of remote sensing. The only difficulty of it now is the SAR and optical image matching. Okay, that's basically a part that has not fully been solved, right? We can measure these points in SAR data very well. We can get for an image for an area tens or hundreds of ground control points, or of control points, doesn't matter, right? Now, if we can match the SAR image to the optical image, we can match that ground control point, the coordinates from that point to the optical image. And at that stage, we can automatically correct them and geocode, auto-rectify all of these optical images in a completely automated workflow without ever touching the ground of an area. So that is very, very useful. And it's actually a well-selling product. So quite of an unknown product, but it's a very well-selling product and good business there. And it's supposed to get even more very, very interesting now with updates in automated driving and all the automated driving companies. What they need is updated map material, continuously updated map material in better than decimeter or around decimeter quality and accuracy. So they are very much interested in that to keep their maps automatically worldwide and up to date. All right. Okay, so let's take a stop here before we come to that huge topic of interferometry. Let's see, do we have some questions so far? Sishan, do we have some questions?
Yeah, we have questions, Professor.
Okay. Right, I stopped sharing. Okay.
Okay, share my screen. Okay. Okay. Yeah, here. Can you see?
Okay. I can see, yes. So let's see. Okay. All right, there's another question on why we are SAR looking rather than Nadia looking. I will not answer that now. It seems that did not get very clear yet. Okay, so I have to spend some slides on that next time. Okay, let me go the next time with several slides and try to explain that more clearly. Okay. What methodology can I apply to correct the atmospheric effects for the INSAR and PS? Right, so that is basically the same what I just showed for SAR Geodesy. Okay, you can use the numerical weather models that are available and you can try to correct effects for that for the INSAR. However, for PS INSAR, you already know what you're doing, right? So some people do not know what I'm talking about now. But for PS INSAR, you can also do that, but ideally we correct the atmospheric effects in PS INSAR based on the data. And that typically works better than with the numerical weather models because they are just not, their resolution is just not good enough. Okay, is it possible using SAR to detect long sunken channels? Yes, it is. And I will show you an example. I have an example actually for that. And I like that example. I will show you. Okay. The next one is really good. Can I use SAR for bathymetry? That's a really good one because the standard answer is no. Okay, the standard answer is no because you can't look underwater. But I saw some work on that which is related that you can see some secondary effects and you can use that to estimate the ground under, like the topography under the water based on secondary effects. So there is some work done in that, but the standard answer is no. Okay, the standard answer is no, and it's I think it's very academic and not really very practical yet. Okay. Can we use SAR data in urban expansion, urban flooding? Yes, surely we can use SAR data for urban expansion. It's very common. For urban flooding, the answer is yes, but the problem that you have is the water, as we identify typically, calm water, we identify it as being black in the image. And now in urban areas, you have the problem that the roads that you're looking at, they're also black in the SAR image. So it's going to be rather difficult to separate the areas underwater from the areas as they normally look like. You can do that, and as urban areas are not only roads and buildings, right? There are many examples where we can see also the floods in urban flooding, but it is more difficult, also because the buildings may block your way and so on. But yes, you can do. The short answer is yes. Okay, do the satellite data providers with raw data and image data both, or only the image data? That's a good question. And the answer is some do, some don't. Okay, so there are satellite data providers who will not give the raw data to you, and there are others who you can get the raw data, right? So this depends. So typically, as a rule of thumb, okay, I would say commercial data providers do not give you the raw data, and the more science-interested data providers, like the European Space Agency, they will also provide the raw data if you really want it. Okay, is there any way to know the looking direction by only looking at the image without prior knowledge? Yes, you could look at the direction of the shadow or the direction of the layover of buildings, for example, right? However, in the metadata of the image that you have, right, that should all be there. And a SAR image without metadata is only of limited use to you. Can the speed, let me check the time. Yeah, okay. Can the speed of moving objects be identified using the effect generated due to its motion? Yes, it can. For the fun of it, I will also show you that next time. I have some slides on that as well. Is the field of SAR imagery data analysis still a hot area to pursue our research career in SAR image data analysis? That depends what you want to analyze, right? It depends what you're looking at. If you go toward target identification, classification, then, you know, with all the deep learning stuff, I would say yes, right? If the angular incidence angle is 0, that's the same like the question above on the Nadia looking. I will come back to that. Ascending or descending influence the far range and near range backscatter value, which is better? No. Right, you're just looking from a different direction. That does not really influence the far range or near range backscattering value. Also, there is not better. They are just different. Okay. Could you please? Now you also mute me. Okay. Could you please explain the relationship between the visibility of the object versus look angle between SAR sensor and the object? No. Right. Why I said no? Because that depends on which kind of object you're looking at, right? Some are more visible from certain angles and others are not. Right. So that is very object and context specific. So there is not an answer that I could put into, you know, one sentence. How many homologous points are required? That's a good point, right? So ideally, well, you need, each homologous point will give you one value for your DEM. So as a rule of thumb, as many as you have pixels in your DEM, okay? Ideally even more, because sometimes you need to interpolate. What is the difference in, I did not see it because of comment, of DEM, DTM, and DSM? That's a very good one. Okay. And I have 1 minute left, and that 1 minute is enough to explain that. Okay. So the digital elevation model, that is the general term. Okay. That explains, that includes all of them. Okay. Digital elevation model. Now, DTM and DSM, they are not identical. So DSM is the digital surface model. That is the height of the surface. So, and DTM is the terrain model. That's the height of the ground. And that is not identical, for example, in a forest area. If you go in a forest, the DSM will be on the top of the forest, and the DTM, the value will be on the bottom of the forest, on the ground. Okay. And both of them are digital elevation models. Both are DM, but they are not the same. Okay. One is a DSM, is modeling the surface, and one is a DTM, modeling the terrain, modeling the ground. And what we typically get from remote sensing mostly is we get DSMs, and what most users want are DTMs. Okay, most users want a DTM, a digital terrain model, and what we get from most remote sensing models are DSMs, and there is then some processing required, and sometimes it's also not directly possible to get from a DSM to a DTM. So DSM again is digital surface model, whereas the surface, for example, top of canopy, and DTM is the digital terrain model, so the ground where you are on the terrain. Okay, I did not answer all the questions. There are also some questions left on the list. I will do that again next time. Some I want to explain more. Some are still on the list, and some I have some cool pictures to show you. So I will do that. Okay. And hopefully then you can understand them more. I see I need to explain you more why you cannot look down, why it doesn't work. That's very basic. Okay. And it's very important that you all get it. Okay. So I'm going to spend more time on that again. All right. Doesn't matter. And if I need to do it again and again and again, we will get there together. Okay. All right. Thanks for joining. Now we had yesterday and today. Now we need a little bit break. Okay. I think next time is on Friday, if I'm right. So we have a little bit break, and then we go deep into SAR interferometry, which will keep us the following lectures. That is, yeah, it's actually not such an easy topic, SAR interferometry. I have to tell you that. But don't be afraid. We will get through that as well, and I hope you will at the end understand it. Okay, great seeing you. I'm happy so many people still joining, and I'm even more happy that I get so many good questions. That makes it much more fun for me. Okay, have a good night. Have a great day, wherever you are.
Thank you so much, sir. Thank you so much.
Nice to see some.